All right, welcome to 5.6, the culmination for us of Chapter 5 and of the entire linear algebra course. So hey, you made it to the last section. So this section is on discrete dynamical systems. So discrete means it goes step by step rather than sort of a continuous set of inputs. Dynamic just means it changes, of course. So discrete dynamical systems, we've already looked at a few examples of those so far. When we were looking at transition matrices and steady state vectors that went with them, or Markov chains, or even the opening example of Chapter 5 with the spotted owl and the stage matrix that was there. So really we're looking at any situation where you have a matrix and you multiply it by an input, get the output, and then iterate, put the output back in as the new input and get the outputs beyond that. So we have, suppose we've got some sort of matrix like this, and we have some sort of input or initial condition, right? You typically would call this something like your x1 or maybe even x0, depending on how you want to order things, and this is your A matrix. So when you multiply the two of them together, then you get the next version of X. So if we do this matrix times this input, then we get 1.7, 2.9. And that would be considered our X1. And so the next round, you'd multiply A by x1, and that would give you x2, and away you go. You can do that as many times as you want and predict long-term behavior. And as we've seen in previous sections, sometimes the result is a steady state vector. Sometimes it spirals off in one direction or another. Let's see, let's just do one more iteration here. We would do the original transition matrix times our new result, and that gives us 1.48 and 2.92. And 2.92. Okay, so that was x1 times the transition matrix. That gives us our x2. So this is the basic idea for discrete dynamical systems, is you will always have an A times an X sub K, which gives you your X sub K plus 1, gives you the next X. And of course, as you do this long term, another way, so you can say A times x1 gives you x2, and then A times x2 gives you x3, and so on. Of course, x2 is the same thing as ax1, so these two lines are the same. Or a squared times x1 would give you x3, and in general, if you want to go 5 steps down the line, you would multiply by a 5 times. And we can do that directly, but we can also take advantage of the power of eigenvalues and eigenvectors. So let's take a look at a different example. Let's just say in general that if we want to do a to the 10th times x1, I guess, so that would take us to a to the 11th, or sorry, x to the 11th, x11 is what I'm trying to say, x sub 11. So we could do that by multiplying by the matrix 10 times, but that's expensive computationally. And it doesn't really help us analyze what happens as time goes on toward infinity. If we take advantage of eigenvalues and eigenvectors, we can analyze long-term behavior rather than just getting a specific point in the future. So this would, of course, mean multiplying by a 10 times, but let's assume that we could write x1 as some combination of the eigenvectors of A. So if we can do that, if we can write x1 as, say, I'm just making up numbers here, 3 times the first eigenvector plus 2 times the second eigenvector. If we can do that, then multiplying a times x1 is the same as multiplying a times 3v1 plus 2v2. We know because this is linear algebra, matrix multiplication is linear and we can factor constants, so this is the same thing as 3 times a times v1 plus 2 times the matrix a times v2. And we also know that multiplying by the matrix A, multiplying an eigenvector by the matrix A, is the same thing as multiplying by the eigenvalue. So this is the same as 3 eigenvalue for v1 plus 2 eigenvalue for v2. So at the moment, that's just a times x1. So this has been equal to x2 all along. Oops, x2, x2, x2. But of course, we're interested in iterating this over the long run. So now if we want to multiply this by a to get x3, so a times all of that would make x3 for us. I'm going to do the same thing again. I'm just going to say it's a times this first clump and a times the second clump. And multiplying a by the first clump is the same as multiplying lambda 1 by the first clump. So this really just simplifies down to, oh here, maybe I should write the inside part first. So this would be a 3a times lambda 1 v1 plus 2a times lambda 2 v2, but a times an eigenvalue is the same as, sorry, times an eigenvector is the same thing as eigenvalue times the eigenvector. So this is the same thing as multiplying by the eigenvalue twice and multiplying by the other eigenvalue twice. Oops, twice. Equals x3. And in general, if I want x to the 10th, so notice the index, 1 greater than the power, so this would be 3 first eigenvalue to the 9th, v1, plus 2 second eigenvalue to the 9th, v2. And this is very easy to change to the 1000th iteration or the 10,000th, or really, as we know from calculus, to look at the limit as the index goes to infinity and see what happens over the long run. So let's go back to our previous example, to this guy right here. And rather than just multiplying by 2, 3 and going from there, let's find the eigenvalues and the eigenvectors and use that to analyze long-term behavior. So we know how to do eigenvalues and eigenvectors by now. I'm going to put the video on pause for a second and write out a few things so you can at least see them, but you won't have to chew up a bunch of time watching me do them, and then we'll talk about where we go from there. Okay, so there's the eigenvalues. I thought we would maybe do the eigenvectors live, or at least one of them. So let's start with the eigenvector for the eigenvalue 1.2. So subtract 1.2 from the main diagonal and augment zeros on the end. So 0.7 minus 1.2 is negative 0.5, 0.1, 0, then we have negative 0.5, 1.3 minus 1.2 is 0.1, 0. And there again we see that thing that's easy to see with real numbers and hard to see with complex numbers. But when you solve for an eigenvector, you will have a free variable. That's how you have an eigenvector, aside from the 0, 0. Okay, so certainly if you want, you can subtract and get that row of zeros on the second line. But really the main point here is that both lines contain exactly the same information about x1 and x2. So we should be able to solve and say x1 is 1/5 x2, and x2 is free. x2 is x2. So any multiple of 1/5 1 is the eigenvector for 1.2. And even though 1.2 is a decimal, I still like working with whole numbers when I can, so I'm going to choose x2 to be 5. So I'm going to get an eigenvector here of 1, 5. That goes with the eigenvalue of 1.2. Okay, you don't need to see me do the other one, so I'll put the video on pause again for a second. Okay, so we have our two eigenvectors of 1, 5 and 1, 1. Right there and right there. Keep in mind, back in the original problem, here comes the mess. Oops, that's not the mess I wanted. There we go. The original problem, our starting vector was 2, 3. So let's see if we can rewrite 2, 3 in terms of our eigenvectors. So let's say 2, 3 must be able to be rewritten somehow as some combination of 1, 5. Some combination of 1, 5 and 1, 1. And of course that is just a system of equations to solve. So augmented row reduced matrix. Oops, come here. So let's see, we wanted those, and I like my equal signs on the right for some reason. So let's see, I want reduce a 2 by 3 matrix. That would be 1, 5, 1, 1, 2, 3. So it looks like 1/4 and 7/4 are the combinations that we need. So 1/4 of that and 7/4 of that. Just a quick check. Let's see on the top, that would be 1/4 plus 7/4 is 8/4, that's 2. And on the bottom, 5/4 and 7/4 is 12/4, which is 3. Okay. That is a correct rewriting of our original x in terms of the eigenvectors of our matrix A. So now, instead of multiplying this by 2, 3, and going on from there, I am going to multiply instead I'm going to multiply it instead by this combination of the eigenvectors, which still does make the same starting condition. We're still starting at 2, 3. Just writing it in an expanded form. So that should still come out the same as it did before. And we know, I'm not going to keep writing that matrix out, let's call that A again. So we know we're looking at 1/4 A times 1/5 plus 7/4 A times 1/1. And we do know that multiplying A, the matrix, by 1/5 is the same thing as multiplying 1.2. by 1/5. And multiplying A by the other eigenvector is the same thing as multiplying 0.8 by the other eigenvector. If you want to crunch those numbers out, you will find that we got the same result as we did before. And just as a quick check, there was our original version where we just did the transition matrix times our starting values of 2, 3. That came out 1.7, 2.9. And now if you use this form that I have right here, instead of the matrix using eigenvalues and eigenvectors, you get 1/4 times 1.2 times anyway, you get 1.7, 2.9. It comes out the same. And you're like, great, Abel, so far you've found a harder, more complicated way to go from x1 to x2. And if you're just doing one step, you are absolutely right. This is harder and more complicated. And we had to find eigenvalues and eigenvectors to do it. But now the power comes in, of course, because if I want to go to the next step, if I was doing matrix multiplication, I'd have to matrix multiply again. So I'd have to take, let's see, where are we? I'd have to take this and do 1.7, 2.9. And find out that's what comes out next time. Or, in this form, I just need to raise this to the second power. And that to the second power. And get the same result. Let's do the matrix twice. Do the eigenvalue eigenvectors twice. And again, even on 2 steps, or really even on 10 steps, there's not a huge advantage, but we can now see what happens over the long run, essentially as x goes to infinity. Keep in mind, as x goes to infinity, that a term like 0.8, so here, maybe we should go back to here. So as the number of steps approaches infinity, this is not really proper notation, but this is basically what's happening, right? We're getting 1.2 to higher and higher powers. And 0.8 to higher and higher powers. I need to move my face out of here. And keep in mind what happens to 0.8 as you multiply it by itself over and over and over and over again. This term, let's see, you need a different color. 0.8 is less than 1, so the higher and higher powers of 0.8 approaches 0. So over the long run, this whole term is going to approach 0. And over the long run, we are just going to be looking at this. So this is our growth term. So we are going to grow by 20% basically every time. We're going 1.2 times what we had last time. And the ratio between whatever these things represent, if this is foxes and hares from that predator-prey system, or if this is different sectors of an economy, whatever we're looking at, they are going to grow at a ratio that stabilizes at around 1:5. 1 to 5, I should say. 1 of this to 5 of that. Growing at 20% per step. And that's at least how it looks for starting at 2-3. It may be different if we start at different starting values, but as we have noticed in the past, starting values don't necessarily affect the long-term behavior. All the starting values affect really are the 1/4 and the 7/4, but they don't affect the eigenvalues. So this term's still going to drop to 0. This term's still going to grow at 20% per year, and there's still going to be a ratio of 1 to 5 between them. It might just be a different scaling factor out front for different starting values. Okay, so I think we've got the basic idea here. In the next video, we should look at another example, look at what this looks like graphically, and also talk about what if there are complex eigenvalues and eigenvectors.